Hi there, welcome to ExamPadi. Our topic today is gravitational fields, and in this lesson we will 1. Explain the concept of gravitational fields. 2. Discuss Newton's law of gravitation and Kepler's law of planetary. 3. Describe the components of gravitational fields and expatiate the relationship between components using mathematical representation. 4. Solving simple problems relating to gravitational fields. And 5. Explore natural and artificial satellites and outline their distinguishing features. As you may be aware, gravity is one of the most important forces in the universe. Think of a gravitational field as a key concept in physics, particularly in the theory of gravitation, which describes an object's influence on producing a force on other objects. Let's take a look at the concept of gravitational fields. The popular legend Isaac Newton suddenly discovered the law of universal gravitation when an apple fell from a tree and hit him on the head as an element of truth. A more probable account is that he was walking through an orchard and wondered why all the apples fell in the same direction with the same acceleration. Great importance is attached to it because Newton's universal law of gravitation and his laws of motion answered very old questions about nature and gave tremendous support to the notion of underlying simplicity and unity in nature. As we continue this learning journey, I will refresh your memory on what a force connotes. In physics, a force field is a region where a test object will experience a force. This force can either be a gravitational, electromagnetic, or another type of force. For example, the gravitational force field around a planet is the region where objects will experience the force of gravity. How would you describe a gravitational field? A gravitational field is a region in space around a mass where another mass would experience a gravitational force. Essentially, it describes the influence of the mass on the space around it. In a nutshell, it is a space around a mass in which the gravitational force of the mass can be felt. Gravitation is the force of attraction a body exerts on all other bodies in the universe. Gravitational force acts between all masses, holding planets, stars, and galaxies together. Fun fact: each mass has a gravitational field around it. Let's dive into Newton's law of universal gravitation. According to Isaac Newton's law of universal gravitation, every point mass attracts every other point mass in the universe, with force directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. It also states that every particle in the universe attracts every other particle with a force proportional to the products of their masses and inversely proportional to the square of the distance between them. This gravitational force is given by the equation as displayed in this diagram. F equals G multiplied by m1 m2 divided by r squared, where F is the gravitational force between the masses. G is the gravitational constant, which is approximately 6.674 times 10 raised to the power minus 11 Newton meter square per kilogram square. M1 and M2 are the masses of the objects, and R is the distance between the centers of the masses. Kepler's law. Hundreds of artificial satellites orbit the Earth together with thousands of pieces of debris. The moon's orbit around Earth has intrigued humans from time immemorial. The orbits of planets, asteroids, meteors, and comets around the sun are no less interesting. If we look further we see almost unimaginable numbers of stars, galaxies, and other celestial objects orbiting one another and interacting through gravity. All these motions are governed by gravitational force. The orbital motions of objects in our solar system are simple enough to describe with a few fairly simple laws. For instance, the moon orbits the Earth in a slightly elliptical path, taking approximately 27.3 days to complete one full orbit. Based on the motion of the planets about the Sun, Kepler devised a set of 3 classical laws called Kepler's laws of planetary motion that describe the orbits of all bodies satisfying these 3 conditions. The first condition is the orbit of each planet around the Sun is an ellipse with the Sun at one focus. Secondly, each planet moves so that an imaginary line drawn from the Sun to the planet sweeps out equal areas at equal times. And lastly, the ratio of the squares of the periods of any 2 planets about the Sun is equal to the ratio of the cubes of their average distances from the Sun. What are the components of gravitational fields? The components of gravitational fields are as follows. 1. Gravitational field intensity. Gravitational field intensity at a point is the force per unit mass of an object placed at that point. That is, mathematically, small g equals F over m. The unit is Newton per kilogram. It is a vector quantity and it is regarded as acceleration due to gravity, where small g equals gravitational field strength, Newton per kilogram. F equals force due to gravity or weight in Newton, and m equals mass in kilogram. 2. Gravitational potential. The gravitational potential at a point is the work done in taking a unit mass from infinity to that point. The unit is joules per kilogram. The gravitational potential V is given by V equals minus gm over r. M is the mass producing the gravitational field, and r is the distance of the point to the mass. The gravitational potential decreases as r increases and becomes 0 when r is infinitely large. The negative sign indicates that the potential at infinity, that is 0, is higher than the potential close to the mass. Number 3. Escape velocity. Escape velocity is a fundamental concept in astrophysics and space exploration. It refers to the minimum speed needed for an object to break free from the gravitational field of a celestial body, like a planet or moon, without further propulsion. To overcome Earth's gravitational pull, the satellite carrying rocket must achieve a certain velocity known as escape velocity. Escape velocity depends on the mass of the Earth and the distance from its center to the rocket's starting point. If m equals the mass of the Earth and the small m equals mass of the satellite, then the gravitational force of the Earth on the satellite is VE equals square root of 2gm divided by r, where VE is the escape velocity, g is the gravitational constant, m is the mass of the celestial body, and r is the distance from the center of the body to the point where escape is occurring. Let's discuss the relationship between acceleration due to gravity and the gravitational constant. If the force of attraction F between 2 particles of matter separated by a distance r is given by F equals gm1 m2 divided by r squared as equation 1. Also recall F equals mg, that is from the formula of force, by substituting F with mg in equation 1. mg equals gm1 m2 divided by r squared. Acceleration due to gravity g equals gm1 m2 divided by r squared multiplied by the inverse of m2. m2 dividing both sides, we'll have g equals gm1 over r squared. Therefore, acceleration due to gravity g equals gravitational constant g times m divided by r squared, where m1 is the same thing as m. Note that m1 is the mass of the body exerting the force on the other unit, e.g. the earth. Let's solve simple problems related to gravitational field. Example 1. Given two masses, m1 equals 2 kg and m2 equals 3 kg, separated by a distance of r equals 4 meters, calculate the gravitational force between them. Using the formula F equals gm1 m2 over r squared, the gravitational force F between two masses is given by Newton's law of gravitation. Given that m1 equals 2 kg, m2 equals 3 kg, and r equals 4 meters. Substitute these values into the formula. F equals 6.674 times 10 raised to the power minus 11 Newton meter square per kilogram square, multiplied by 2 kg multiplied by 3 kg divided by 4 meters square. Calculate the result. F equals 40.044 Newton meter square multiplied by 10 times 10 raised to the power minus 11 divided by 16 meters square. Our final answer is 2.50275 times 10 raised to the power minus 11 Newton. Example 2. Given a point mass m equals 4 kg and a distance r equals 3 meters, from the center of the mass, calculate the gravitational field strength at that point. The formula for gravitational field strength around the point mass is given by G equals gm over r squared, where G is the gravitational constant. Substituting the given values, G equals 6.67 times 10 raised to the power minus 11 Newton meter square per kilogram square, multiplied by 4 kg divided by 3 meters square. G equals 2.97 times 10 raised to the power minus 11 Newton per kilogram. Therefore, the gravitational field strength at a distance of 3 meters from the center of the mass is approximately 2.97 times 10 raised to the power minus 11 Newton per kilogram. Example 3. Calculate the escape velocity for an object on the surface of the Earth. Given the mass of Earth m as 5.97 times 10 raised to the power 24 kg and the radius of Earth r as 6.37 times 10 raised to the power 6 meters. The formula for escape velocity VE equals square root of 2gm divided by r, where g is the gravitational constant, m is the mass, and r is the radius. Substitute the given values. V escape, or the escape velocity, equals 2.67 times 10 raised to the power minus 11 Newton meter square per kilogram square, multiplied by 5.97 times 10 raised to the power 24 kg divided by 6.37 times 10 raised to the power of 6 meters. By calculation, escape velocity equals 1.12 times 10 raised to the power of 4 meter per second. Therefore, the escape velocity from the surface of Earth is approximately 1.12 times 10 raised to the power of 4 meter per second. Let's differentiate between artificial satellites and natural satellites. Natural satellites is an astronomical body that orbits a planet, dwarf planet, or small solar system body. The most common natural satellites we know of are the moons. For example, the moon is a natural satellite of the Earth. Besides the moons of the planets, some other natural satellites are also moving around the sun. This includes asteroids, comets, and meteoroids. Artificial satellites. These are man-made objects that are intentionally placed into orbit. Thousands of artificial satellite orbits Earth. They have a variety of uses, including weather forecasting, surface imaging, communication, and navigation. Artificial satellites are launched into space to perform specific tasks, such as studying the Earth's atmosphere, monitoring weather patterns, or facilitating communication between different parts of the world. Lastly, in this lesson, we will discuss the distinction between natural and artificial satellites. 1. Artificial satellites are created and launched by human beings, while natural satellites are naturally occurring bodies that orbit celestial bodies, typically planets. 2. Artificial satellites are manufactured on Earth and launched into space using rockets, while natural satellites are formed through natural processes such as accretion in the early solar system. 3. Artificial satellites are used for communication, weather monitoring, scientific research, and navigation, whereas natural satellites serve various purposes, including gravitational influences, tidal effects, and geological interactions. 4. Artificial satellites generally have negligible impact on the gravitational dynamics of their parent body, whereas natural satellites can significantly influence the parent body rotation, tides, and geological activity. And 5. Artificial satellites are subjected to international regulations and agreements to avoid collisions and space debris issues, whereas natural satellites are governed by natural laws with no external regulations. We have come to the end of today's lesson. Answer the following questions to assess yourself. 1. Define gravitational field and discuss two of its components. 2. Give a summary of Newton's laws of gravitation and Kepler's law of planetary motion. 3. Using mathematical representation, show the relationship between acceleration due to gravity and gravitational constants. 4. Give 3 differences between artificial and natural satellites. 5. Calculate the escape velocity for a rocket fired from the Earth's surface at a point where the acceleration due to gravity is 10 meters per second squared and the radius of the Earth is 6.0 times 10 to the power of 6 meters. Thank you for learning about gravitational field with me. I believe you have learned 1 or 2 things. See you in our next video. Bye.